Hello everyone, this is Hu Wenbo, a PhD candidate from the Chinese University of Hong Kong. Today I'm going to share with you our work, Conditional Directed Graph Convolution for 3D Human Pose Estimation. This work was done in collaboration with Dr. Zhang Changgong, Dr. Zhan Fangneng, Professor Zhang Lei, and Professor Wang Tianxin. Human pose estimation plays an important role in many applications, such as action recognition, data-driven computer animation, athletic training, and so on. Current 3D human pose estimation approach typically divides tasks into two stages. The first stage is 2D pose estimation to localize the key points in the image space. And the second stage is predicting joint positions in the 3D space from 2D pixel locations. We also follow this strategy and focus on the second stage. The problem is challenging due to the ambiguity of 2D to 3D lifting and the high nonlinearity of human dynamics. To relieve the challenges, our key idea is to leverage the prior knowledge of human poses. Hierarchy is a significant characteristic of human anatomy. For example, when a person moves the shoulder joint, the following joints that are elbow and wrist are moved as well according to the articulation. Hierarchy is widely utilized to represent human motion in computer animation, as evidenced by the BVH file format. To utilize this property, we propose to represent the human skeleton as a directed graph. By doing so, the hierarchical relationships are explicitly presented by the directions of edges. On the other hand, we observe that there is non-local dependence among joints, and more importantly, the non-local dependence is conditioned on the input poses. For example, the dependence between left hand and right foot joints is obviously high when people are walking, since this pose can help keep balance. In contrast, the dependence between hands and head would be significant when people are eating. Inspired by this, we propose a spatial temporal conditional directed graph convolution to condition the connections of the directed graph on input poses, such that different kinds of poses can adopt appropriate connections to optimally leverage the non-local dependence. Here shows the overview of our method. Given a sequence of human poses in the 2D image space, we first construct a temporal sequence of directed graphs. The input 2D poses can be obtained by any of the shelf 2D pose estimators. The features associated with nodes and edges are initialized at the joints locations and their first-order derivatives, respectively. After this step, the problem now lies in how to extract features to estimate the 3D pose. To this end, we use 5 types of blocks in our U-shaped conditional directed graph convolutional network, named CondDGConv. The first kind of block is spatial temporal directed graph convolution. It consists of a directed graph convolution followed by a temporal convolution. Among them, directed graph convolution exploits the spatial relationship, while the temporal convolution is to utilize the temporal relationship. The second kind of block is spatial temporal conditional directed graph convolution, which is designed to condition the connections of the directed graph on input poses. As shown here, there are a series of tunable connection matrix spaces E1, E2, E3, and En. To differentiate input samples, we use a routing function to predict the blending weights from the output of previous layer. After that, we linearly combine the bases by the predicted blending weights to produce the conditional connections, which are then fed into the conditional directed graph convolution to aggregate the spatial information both locally and non-locally. Finally, a temporal convolution is employed to aggregate the temporal information. Besides above two major blocks, the other three types of blocks can be easily derived. The temporal downsampling block is setting temporal convolution strength to 2. It is used to downsample the temporal resolution for larger receptive fields. The temporal upsampling block is a conventional bilinear interpolation along the temporal axis to recover higher temporal resolution. The FC block is a standard fully connected layer to predict the final 3D pose from the extracted features. Now let's dig into the key operator, conditional directed graph convolution, and then the directed graph convolution can be derived from it. As shown here, the input-directed graph has predefined connections shown as black arrows and predicted conditional connections shown as blue dashed line arrows. The conditional directed graph convolution can be formulated with 3 steps. The first step is node updating. Connections used in this step are predefined. For each node Ni, we have the set of incoming edges and the set of outgoing edges. Take node N4 as an example. The incoming edge set is E3 and the outgoing edge set is E4 and E5. Following the idea of conventional convolution, aggregating neighboring features, the node's updating is defined as the aggregation of its incoming edge set, its outgoing edge set, and itself. However, the number of elements in the outgoing edge set is varying. Therefore, we employ a pooling function to summarize features of the outgoing edge set. After the node's updating step, features associated with all the nodes are updated. The second step is node updating with conditional connections. It is designed to address the varying non-local dependence. Thus, connections used in this step are predicted conditional connections. For each node Ni', we have the parent node set and the child node set. For example, node N4' have the parent node set N2' and the child node set N3'. Similarly, we define this step as the aggregation of its parent node set, child node set, and itself. The third step is edges updating. Similarly, we formulate this step as aggregation of the source node, target node, and itself. After these 3 steps, features associated with both nodes and edges are updated. Note that even the edges updating step adopts the predefined connections. The non-local information can also be aggregated into the edge features, since they are updated by the source and target nodes features, which have aggregated the non-local information. Removing step 2 can yield the directed graph convolution, which is purely based on the predefined connections. Thus, it can better utilize the prior knowledge of human skeletons, but fails to leverage the non-local dependence. Okay, now let's see some qualitative results. We compared our method against the baseline, UGCN, which is based on undirected graph convolution and without conditional connections. To better visualize the difference, we overlay the ground truth 3D poses in neutral gray as a reference, and show various viewpoints. We can see our results are more accurate, especially for the end effectors, such as the wrist and ankle joints. It qualitatively demonstrates the effectiveness of our method. Furthermore, to better visually evaluate the results, we show some example videos here. We can see results of our method are more consistent with the ground truth. Although we quantitatively compared our approach with top methods on the human 3.6 million benchmark using Protocol 1 metric, including image-based methods and video-based methods. The input total poses are estimated from monocular images or videos by CPN or HRNet. We can see that our method consistently outperforms all the others by a large margin, no matter with CPN or HRNet input total poses. This demonstrates the effectiveness of our proposed conditional directed graph convolution. Please refer to our paper for more details. The QR code here is linked to our project webpage. And welcome to our poster session for further discussion. Thanks for your attention.